In the previous part, we have discussed about the Coulomb's law as well as the force on the charges, and the last part we have discussed the superposition of the electric forces. Now we'll discuss about the force due to a continuous charge distribution. First, I will explain what is a continuous charge distribution. See, previously, whatever the force we have calculated, that is due to the point charges. But if the charges are not seems to be a point portion, it is distributed just like assume this type of portion. It may be a surface, it may be a volume. Then how we can able to find out the force due to this charge distribution at a certain point? Okay, so for this region, assume I want to find out the force at P point. So what we have to do here, we'll assume a smaller portion here, a very small portion, and we have to assume that the charge of this small portion is dq, and the force we have to apply at point P, there I have to keep one charge. That charge we have taken q naught. Okay, so from this portion to P point, that distance we have taken r. Okay, its magnitude is r, and the vector, the unit vector along this direction, we have taken r cap. Okay, now if I want to find the force on q naught due to this small charge dq, so there I have to apply Coulomb's law. So as per Coulomb's law, we know that small force, why it is small, because we are taken for a small charge, so df is equals to 1 by 4 pi epsilon naught q naught into dq by r square. If I want to find out the force due to the whole charge distribution, so for whole we have to integrate it. So f equals to integration of df, and integration of df equals to integration of 1 by 4 pi epsilon naught q naught dq by r square. See, q naught, 4 pi epsilon naught, everything is constant, just take it out. So q naught by 4 pi epsilon naught integration of dq by r square. So this is the equation of force if I want to find it out in a form of continuous charge distribution. Okay, so this will be the equation. Now we have to see some example here. So let's see, the charge is distributed over a volume. Okay, so how we can able to find out the force? So number one, we have to see that volume charge distribution. Okay, so let's see, assume this is an object which is having a certain volume v. Okay, and the total charge is distributed here, that is q. Okay, here we have to find a force at point P if a charge q naught is kept there. Okay, so we know the equation of force F equals to q naught by 4 pi epsilon naught integration of dq by r square. Now we have to find dq. How we have to find it? So let us assume a smaller volume here. So as we are talking about a volume, so we have to assume a smaller volume dv. So in smaller volume dv, there should be a smaller charge dq. How we can able to find it? So to find it out, we have to write down the charge per unit volume. So charge per unit volume. Okay, so what is charge per unit volume here? That is, total charge is q, total volume is v, so charge per unit volume is q by v. That is denoted by rho. This charge per unit volume is denoted by rho. So charge in dV, if we have taken it is dq, that should be, okay, that should be rho into dV. So if for unit volume it is rho, for dV volume it should be rho dV. So instead of dq we have to write down rho dV. Okay, so let's see. So if force equals to q naught by 4 pi epsilon naught integration of, instead of dq we have to write down rho dv by r square. Okay, so we have already assumed that this distance is r, okay, whose magnitude is r here. Okay, it is acting in this direction. If I want to write it down in vector form, so it should be r cap. Okay, so if a charge is distributed in volume, we can able to find it out by this way. Now we have to go to the next part. If the charge is distributed on a surface, so next thing is surface charge distribution. Surface charge distribution. So assume a sheet, okay, aluminum, assume a insulated sheet, okay, insulated page, whatever the page we have seen here. Here the charge is distributed. Assume this is a surface where the total charge is being distributed. So the total charge is q, and as it is distributed over a surface, so we can assume the surface is a. So it is clear that we have to find out charge per unit area. Charge per unit area. So charge per unit area, how much? That should be q by a, and it is denoted as sigma. Next, we have to find a smaller area ds. So from ds, at a distance of r, at a point P, we have to assume a charge q naught is there. So we have to find the force on it. So before that, we have to find out the charge on ds. If we have taken it is dq, so the value of ds will be sigma into ds, the value of charge dq in ds. Okay, so if I want to find the smaller force, so df equals to, we have already find it out, 1 by 4 pi epsilon naught q naught into dq by r square r cap. Okay, if I want to find out the force, it should be 1 by 4 pi epsilon naught q naught integration of dq by r square. Instead of dq, we have to write down sigma ds. So f vector should be equals to q naught by 4 pi epsilon naught integration of sigma ds by r square r cap, where r cap is the unit vector along the direction of r. Okay, surface charge distribution. Next we will go for linear charge distribution. Assume if the charge is distributed just like the pen we have seen here, on that pen, if the charge is distributed, then how we can able to find out the force at a certain distance. So next one is linear charge distribution. Okay, so first of all we have to assume a linear portion, assume a where, okay, definitely it is an insulator where the charge we are assuming it's positive charge. Okay, everywhere we are assuming positive, because if we assume negative, then unnecessary we have to apply a negative sign, which we don't want to do. So here the total charge is distributed. Previously we have taken q, the total length is l, you are assuming. So a smaller length we have assumed here, that is dl, and from dl at a distance of r, okay, at point P, one charge is kept, that is q naught. So for dl we have to find the charge, that is dq. So that for that reason we have to find out charge per unit length. Okay, so charge per unit length is Q by L. So Q by L is equals to lambda. Okay, and for dl, charge dq equals to lambda into dl. So directly I can write down force F equals to q naught by 4 pi epsilon naught integration of dq by r square r cap. Instead of dq we have to put lambda dl, that is q naught by 4 pi epsilon naught integration of lambda dl by r square r cap. Okay, so these are the continuous charge distribution, that if the charge is distributed in a continuous form. Now we'll just go to the next and important part, by which the heading also given, that is electric field. Till now the thing we have discussed, that is all about electric charge, and if the charge is distributed by different way, how we can able to find the force. Now we have to find what is electric field. So before understand the electric field, I just make you remember that in class 10 you have learned about bar magnet. Before class 10 also you have done it earlier. So where we have kept one bar magnet, we have seen around the magnet one zone, okay, one area is created where the influence of this bar magnet is sustained. Okay, and that zone is known as magnetic field. So similarly, if I have kept one charge, if I have taken a positive charge only, so around itself a zone is created where the influence of the charge is sustained. If another positive charge come in this zone, it will repel this positive charge. If another negative charge has come here, it will attracted by this charge. So that zone is known as electric field. So if I want to define it, it is written that the space around any electric charge in which the influence can be felt, so that any other charge in that region is acted upon by the force, is known as electric field. And now the question has come, how we can able to measure it. So for measuring, we have to find out force per unit charge. So that I will explain. That assume if a force applied on one charge, assume one charge is kept here, it is Q. At a certain distance, one charge is kept, that is Q naught. If it is at a distance, somehow it is distance there, so there will be a force applied by the charge Q on Q naught, and similarly same force is applied by Q naught to charge Q. Here we are only talking about the charge Q, we are not discussing about the force by Q naught. So this force will acting in this direction because it will repel it. So instead of Q naught, listen to me carefully, instead of Q naught, if I have taken one unit charge, that if Q naught is equal to 1, then the force is applied by Q should be equal to the electric field. Okay, if I want to show you experimentally, let's see. If the distance is r, simply we can write down the force should be q naught by 4 pi epsilon naught r square. That's a simple thing. Okay, and if I want to show the force, it is force by q on Q naught by Q, that should be r cap, because it will repel in this direction. And now if I want to find out E, I have to put Q naught equals to 1. So if Q naught equals to 1, then okay, then F should be Q by 4 pi epsilon naught r square r cap. Okay, similar thing we'll get if q naught I divide here also. Just see it. If it is written by this way, that is f vector by q naught, that is also similar, that is q by 4 pi epsilon naught r square. This one is known as E or electric field. So electric field is basically force per unit test charge acting at a vanishing small positive test charge placed at a given point. Why it is told vanishing? Because whenever we have to write about electric field, that electric field equals to E equals to limit Q naught tends to 0, because the value of q naught, that charge we have assumed, that is very small, that value is tends to 0, f vector by q naught, that is your electric field. So it is force per unit test charge. So here test charge is q naught. Okay, test charge is q naught, that is our electric field. So as force is a vector quantity, so electric field, it is also a vector quantity. If I want to find out the SI unit from this equation, what will be the SI unit of it? So SI unit, see, force per unit charge, so it should be Newton per Coulomb or Newton Coulomb inverse. Apart from this also another unit is there, that is volt meter inverse. How this unit has come, that should be discussed in potential chapter, the electric potential chapter, it is discussed. If I want to find the dimension, I think you have remembered the dimensions you have read in class 11. So if I want to find the dimension, so it should be force by charge. So force, we know it is m L t to the power minus 2, and charge is basically current into time period. So current is denoted by A, time period is denoted by T. So it will come m L t to the power minus 3 a to the power minus 1. So that is the dimension of electric field. Now our target is to find electric field for a point charge. Okay, I think what is electric field, that is clear to you. It is the space around the charge, and we can able to measure it somehow by this process. Okay, so next our target is to finding out the electric field due to a point charge. Electric field due to a point charge. Okay, how we can able to find the electric field due to a point charge? So very simple thing is there, what we have discussed earlier also. So let a charge q whose electric field you have to find out. So at a distance we have to keep one charge q naught. Okay, at a distance r. So this is the magnitude and the vector is acting in this direction. So this q naught, what we have to keep here, that will be very small. Okay, so if I am finding out the force acting by q on q naught, force on q naught by q, that is f of q naught into q, it will act in this direction because it will repel it. Okay, so how much force will apply? What should be the magnitude? That is 1 by 4 pi epsilon naught q into q naught by r square r cap. And here if I want to find the electric field, so it is f q naught q by q naught, that is equals to q by 4 pi epsilon naught r square r cap, and this is your electric field. Okay, exactly the same thing we have done earlier. So from here we can conclude that electric field also follows the inverse square law, that is E is inversely proportional to the square of distance, just like the force. Okay, so that is the equation of electric field, that is Q by 4 pi epsilon naught r square for a point charge. Next we will discuss that, as you know, the electric field, it is a vector quantity. Similarly, if I want to find out the electric field of a system of charges, then how we can able to do it. So our next target is to see electric field for a system of charges. See, similar thing we have done earlier whenever we have to find out the superposition of force. So if instead of 2 there are various charges, how can able to find the force? Same thing we will do here also. Okay, here we have to take two charges, that is one Q1, another one is Q2, which is the position of R1, and another one which is at the position of R2. One point is given, that point we have to take it is P, and the P is at a distance of RP. Okay, vector definitely. Then if I want to find out the net electric field at P, so for Q1 on P we can write down EQ1. So EQ1 equals to, so this distance I am taking R1P vector, and this is R2P vector. So it is Q1 by 4 pi epsilon naught R1P whole square, and direction should be from 1 to P, that is R1P cap. It will be directed along this direction. EQ2, that is Q2 by 4 pi epsilon naught R2P square R2P cap, acting in this direction like this. And if I want to find out the resultant one, so we have to complete the parallelogram. That will be the resultant electric field. Okay, that is EP. It is EQ1 and it is EQ2. So to find EP, we have to vectorically add these two. Okay, so EP equals to EQ1 plus EQ2 in a vector form. So if you add it, then we can able to find out the resultant EP. So instead of two charges, if there are n number of charges, so EP should be EQ1 plus EQ2 plus dot 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 plus EQN. How many number of charges will come? Their vector sum will be the superposition of electric field. Okay, so if I want to write it down here also, it is Q1 by 4 pi epsilon naught R1P whole square R1P cap, okay, plus Q2 by 4 pi epsilon naught R2P whole square R2P cap, just like dot 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 many apart. So here if I want to write down it, that is in general form, EP should be summation 1 by 4 pi epsilon naught summation of I equals to 1 to n Qi by 4 pi epsilon naught R I P whole square R I P cap. Okay, that is the general form. So just I want to put it in one place, so it is little bit of smaller. So please see and try to understand whatever we have done earlier, exactly the same thing we have done here, that is the vector sum of all the electric field, and by that way we can able to find out the superposition of electric field. By this equation also many more numericals come. So for numerical I have done a special video that I think I'll send it you after some days. Thank you. Next part we will discuss today, that is electric dipole. Okay, so first I'll just make you clear what is a dipole. Assume if two same charges, means the magnitude of two charges are same, only the polarity is different. If it is kept at a certain distance, then this setup, what it is formed, that is known as electric dipole. So same charges means if one side q, another side I am taking minus q. So here it is minus q and here it is q. If it is kept at a distance of 2a, this this whole setup is known as an electric dipole. So by definition it is known as a pair of equal and opposite charges is separated by a distance. Okay, and two opposite charges we have taken minus q and plus q and taking a distance of 2a. Now by this setup, which physical quantity we calculate? Means by a dipole, what the things we want to calculate? We want to calculate here dipole moment. What is dipole moment? By definition, it is told dipole moment is the product of any one of the charge and the separation between them. If I denote dipole moment by P, so it is 2A, the separation into one charge, that is Q, and it is a vector. It is a vector quantity. So P equals to 2A into Q or Q into 2A. It is a vector quantity. What will be the direction? The direction should be negative charge to positive charge. That is a dipole. Means this is the direction of a dipole moment. Okay. Now, what is the unit of dipole moment? By equation only, we can say that the unit should be Coulomb for charge and for distance it is meter. So SI unit is Coulomb into meter. That is your dipole moment. Now the question has come from this dipole, what the things we want to calculate today. So first we have to find out the electric field of a dipole for different position. So our next heading that we have to do now, that is electric field of a dipole for different position. Okay, so what will be the first position where we have to find out the electric field? So first one is known as axial position. Axial position. What is axial position? I'm making you clear. Assume this is a dipole minus q and that is 1 plus q. Okay. If I want to find a electric field at a point P which is in same axis, you see in which axis minus q and q is kept, on the same axis the P is kept there. What will be the distance of P? As there is two charges. Now I will make you clear that why we have taken the separation 2A. What is the reason behind it? I can take it A or L or R, whatever it may be. Why it is 2A? The reason is that when we have measured any distance from a dipole, that is always measured from the midpoint. So from the midpoint O, the distance of P we have taken, it is R, and here so this part remain A and this part remain A, as we have taken it 2A. Instead of it, if I have taken only A, so here it will be A by 2, here it will be A by 2. See, unnecessary a fraction has come. Okay, so to avoid the fraction we have just made this thing that 2A. Okay, Now the question has come, what will be the distance of point P from minus Q? So from minus Q, you see the whole distance, that should be, this is R and this is A. So we can write down it is R plus A. And from plus Q, this distance, it is R minus A, because this one is R and this is A, it is R minus A. So as we have got the distance, we have to find out the electric field separately, and after finding the electric field, we have to add this and then we'll get, okay, what will be the resultant electric field here. So first we have to find out electric field due to minus Q, and that is E of minus Q. It will be Q by 4 pi epsilon naught R plus A whole square. See, here I have not given any sort of sign because it is not needed here. I have to mention direction by this way, as it is acting in this direction. You see, this electric field will acting in this direction by this arrow. Here E minus Q will be acting. So as E minus Q will act in this direction, it will be taking as minus R cap, because it's opposite to the R. And if I want to find out the electric field, okay, due to a charge Q, so for this, here for this it should be Q by 4 pi epsilon naught R minus A whole square, and it is directing in this direction, that is EQ, it is R cap. So here we can mention it is a force of attraction and this is a force of repulsion. Okay, now the resultant electric field will be how much? E equals to E of Q plus E of minus Q. Okay, so E of Q and E of minus Q, if you write it together, then it should be Q by 4 pi epsilon naught, we have to make a common, and then it should be 1 by R minus A whole square minus 1 by R plus A whole square. The minus sign has come due to the minus R cap. Here it is plus R cap, so R cap should be in outside. Okay, now we have to find out, we have to do the calculation. Okay, so this calculation is a bit easier. I'm just doing here the calculation. If I want to do, it is Q by 4 pi epsilon naught, at top it is R plus A whole square minus R minus A whole square by R minus A whole square into R plus A whole square. Okay, whole R cap. Okay, so that will be the part, and if I am taking here, it is E vector is equals to Q by 4 pi epsilon naught A plus B whole square minus A minus B whole square. Simple thing, it's the equation of 4AB. So it should be 4 into R into A by R minus A and R plus A. So it's R square minus A square, its whole square. Now an R cap is in outside, that is obvious. Okay, so here it is Q by 4 pi epsilon naught. What we have been taking today, we have to take, it is 2 into A into 2 into R by R square minus A square whole square, R cap. Okay, so here you see 2A into Q, it is P by 4 pi epsilon naught. Okay, and it is 2R into R cap by r square minus a square. So that should be the electric field at an axial point. If I want to assume one thing, then it is bit easier for us. That is, if r is very greater than a, then r square minus a square nearly equals to r square, and then E will be P by 4 pi epsilon naught 2 into r by its whole square is there, so r square whole square into r cap. So one r will be cancelled out, so it will be twice pr by 4 pi epsilon naught r cube into r cap. Interesting thing is there, for a dipole, the electric field is inversely proportional to r cube, where for a point charge we have seen it is 1 by r square. It is inversely proportional to r square, but here it is inversely proportional to r cube. Okay, that simple thing you have to remember. Okay, now we'll discuss about the electric field at equatorial point. What is the equatorial? That you know, that if we have assumed a dipole here, equatorial means if a straight line just bisect here at midpoint perpendicularly on that straight line, if I assume a point P, so that point is assumed at a distance r from the midpoint. Assume this point is A, this point is P. So from here we have to find out the electric field. Okay, so let's see how it can be done. So similar thing we will do, that we have to find out the distance here. So if it is r and here it is A, so that will be root over of r square plus a square as per Pythagoras theorem. Here also it is root over of r square plus a square as per Pythagoras theorem. So here E minus Q means electric field due to the charge minus Q, that will be Q by 4 pi epsilon naught. This distance is r square plus a square, because we have to square, so as it is root, so it will come r square plus a square. And what will be the direction? Because as it is a minus, so here it will attract it, so this is the direction. Okay, so we can say it is RPA cap. RPA cap, it will act in this direction. If I'm talking about electric field due to a charge Q, so it will act Q by 4 pi epsilon naught r square plus a square RBP cap, because the direction should be here, it is RBP. So along this direction it is E minus Q, and here it is E plus Q. So as the space is small, I'm not able to take much area. So to find the resultant one, how we can able to find the resultant one? So we have to complete the parallelogram, and that will be the resultant one. Okay, see, if I'm talking about the magnitude, both the magnitudes are same. So here we know to represent a vector, we represent by a arrow sign, that we all know from class 11 only. So here, as the magnitude is same, so the length of the arrow sign in both the case it will be same. What is the utility of it? Now if the length is same, then only this resultant electric field, that is E, that should be parallel to the base or to the axis of the dipole. Okay, otherwise it shouldn't be parallel. So that simple thing we have to remember. Now we'll come into the resultant electric field E. So it should be E Q plus E of minus Q. That is the resultant electric field here. Now, how we can able to find it? Let's see. If it is this angle, if I assuming theta, okay, if this angle is theta, so this angle will also be theta, because it is see, the two sides are same. It is isosceles triangle, so as the two sides are same, so as the two sides are same, so two angles should be same. If this angle is theta, so this angle will also be theta. So if I want to show you the component of E plus Q is acting along E, that is E Q cos theta, right? We know the component division. So if this is a vector and this is another vector, if this angle is theta, so the component, assume it is P vector, assume it is Q vector, so the component of P acting along Q, that is P cos theta. Here also it is EQ cos theta. Similarly, if this angle is theta, this angle is also theta. Okay, so as this is theta, so the component of E minus Q acting along E, that is also E minus Q cos theta. So we can say the magnitude of E should be equal to E plus Q cos theta and E minus Q cos theta. And in which direction it is acting, you see, exactly opposite to the direction of dipole, because the dipole is always acting, the dipole moment is always acting from negative to positive, and here it is acting in opposite direction. So first I have to find the magnitude here. So this two magnitude, EQ and E minus Q, both are same, so we can write down it is 2 EQ cos theta. So 2 EQ cos theta, if I put the values here, 2 into value of EQ, it is Q by 4 pi epsilon naught R square plus A square. Now we have to find the cos theta. What is cos theta here? If I assume the triangle PAO, so here you see cos theta equals to A, that is the base, by hypotenuse, that is cos theta equals to A by root over of R square plus A square. So put the value here, A by R square plus A square whole to the power half, as there is a root over. Okay, now just arrange it. Okay, so it is 2 into Q into A by 4 pi epsilon naught R square plus A square. So it is 1, it is half, so it is 3 by 2. That should be our magnitude. And if I want to express it in a form of vector, so we can say E vector equals to minus, we have to take a common, minus P cap. Okay, minus P cap means exactly opposite to the dipole, exactly opposite to the dipole. And now here we have to assume one assumption. What is? Now if R is very greater than A, then R square plus A square is nearly equal to R square. So if I put the value here, that is E equals to twice into Q into A by 4 pi epsilon naught R square into 3 by 2. By the way, this twice Q into A, that is twice A into Q, that means it is P. Okay, so P by 4 pi epsilon naught, you see 2 will be cancelled out, it is R cube. Okay, so here also we can write down that electric field for a dipole in inversely proportional to R cube. Okay, electric field in a dipole is inversely proportional to R cube. So here we have to mention also 2A into Q, we can write down it is P by 4 pi epsilon naught R square plus A square whole to the power 3 by 2 to minus P cap. Okay, this is our electric field at equatorial point. So two things we have to remember. For axial point, it is 2p by 4 pi epsilon naught r cube, and for equatorial point, it is p by 4 pi epsilon naught r cube. Now the thing we will learn today, that is torque on a dipole in a uniform electric field. Torque on a dipole in a uniform electric field. Okay, let's see. Torque on a dipole in a uniform electric field. The thing we have to discuss here, that if one dipole is kept in an electric field, then how we can able to find the torque on here. So why the torque will act on it, that is one question. Let's see, let's find it out. Assume the electric field is acting in this direction, and that is uniform. So as it is uniform, so we can represent it by some equidistant parallel lines. Why we can able to represent by parallel lines, that we have to discuss in the next part, that is electric field lines and flux. Okay, so assume one dipole is kept here. It is minus q, it is plus q, the distance is 2a. So the total for electric field is acting here, it is E. So as the electric field is acting here, so for the different charges, there will be a force, because we have learned that electric field equals to force by unit charge. So from here, force equals to charge into electric field. So how much force is acting on here in charge Q? The magnitude will be Q naught into E. Here, as it is a negative charge, the direction of force is here, minus of Q naught into E. Okay, you see two equal and opposite charge is acting at a certain distance. Remember one part we have learned in class 11. If a force is acting here exactly same and opposite, then in this body the couple is acting. If this point is A and this point is B, so the force into perpendicular distance, that will give us couple or tau. So tau equals to F into AB, that we have learned. Here also we have to find the perpendicular distance and find the couple. Okay, so here we have find out the force equals to Q into E, not Q naught, I'm sorry, it should be Q into E. The force is applied, and the perpendicular distance we have to find out. How we have to find the perpendicular distance? Let's draw two straight line, and they will meet in one point here. This distance, that will be known as the perpendicular distance between the two charges. What will be the distance? If this angle is theta, okay, that means if the dipole makes the angle theta with the electric field, then this distance will be, we have to find it out. Assume it is A, it is B, and here it is C. So you see it's a right angle triangle. So for right angle triangle, we know BC by AB, it is perpendicular by hypotenuse, that is equals to sine theta. So BC equals to AB sine theta, or the value of AB we know it is 2A, so it is 2A sine theta. That we have got the perpendicular distance. So if I want to find the torque tau equals to force into BC. So force, how much? It is Q into E. BC is 2A sine theta. So Q into 2A, 2A into Q into E sine theta. 2A into Q equals to P, that is P E sine theta, that is equals to tau, and that is the cross product. That means tau is equals to P cross E. So if I want to find out the torque on a dipole in an electric field, that will be the cross product of dipole moment and electric field. That means the direction of the torque will be perpendicular both on dipole moment and electric field. Now we have to see some special cases when the torque will be maximum, that is tau max. Now we know for tau max sine theta should be equals to maximum. So sine theta, when it will be maximum, when it is 1, that means theta should be there, it is 90 degree. So theta 90 degree means if the dipole is kept perpendicular. Okay, here it is minus q, here it is plus q. Then the tau will be PE, that is the maximum value. If I want to find out tau mean, then the sine theta will be minimum. Okay, and sine theta minimum means that is 0, and sine 0, how we can able to find? Then theta will be 0 and tau will be 0 here. That means in which direction the electric field is acting if the dipole also aligned in same direction. Okay, then the torque will apply here, that is the minimum torque. Okay, and for that reason we will get the minimum torque is applied on the dipole. Instead of uniform electric field, if the electric field is non-uniform, assume it, if the electric field is non-uniform, then what will happen? So simple thing, as it is uniform electric field, then the same force is applied in 2 points. That's why the body is rotating, the dipole is rotating. If it is non-uniform electric field, then along with rotation there will be a translation. Okay, so we can say both translatory and rotatory motion. Now question will come, in which direction this translation occur? See, simple thing, if minus q in this side, then the force on minus q will be more, so it will translate in this direction. If minus q in this side and plus q is here, then force of repulsion will more, then the body will move in this direction. So this is in non-uniform electric field. If you kept it or put it in a non-uniform electric field, then this thing will occur. Okay, now we'll go to the next and today's last part, we can say that is electric field lines. It is a bit easier for you to understand. See, for the case of magnetic field, to represent it, we have assumed some geometrical lines. Okay, so these geometrical lines are used to represent the magnetic field around a magnet. So similarly, to represent the electric field also, we have assumed some geometrical lines and curves. Okay, and that one is known as electric field lines. So what will be the electric field lines? If anyone asks you, we can say some imaginary geometrical curves, and the tangent of curve at a certain point shows the direction of electric field. Okay, so I don't think it is very much hard for you, because you have already learned it in case of magnetic field. So similar thing is here. Similarly, as like magnetic fields, here also some properties of electric field lines. So what are the electric field lines? So number one, as like magnetic field lines, these are continuous curves. Okay, as like magnetic field lines, they will never intersect each other, because if they intersect, there will be two direction of electric field at one point, which is not obvious and which is impossible. Okay, so this thing will not possible. Okay, the electric field lines will be continuous, they will never intersect. Okay, and if they are more closer, then it is clear the strength of the electric field lines will be more. If I'm talking about their direction, they are always normal to the surface of a conductor. Okay, they are always normal. So by not talking, if I want to express some diagram, then it will be easy for you to understand. See, if it is a positive charge, what will be the electric field? So electric, to find the electric field lines, what we have done, we have just kept one positive charge, one small positive charge nearer to the main charge. Simply to find the magnetic field lines also, what we have done, we have kept a smaller magnetic field, that is a compass. Okay, magnetic needle, we just kept it nearer to the magnet, that's why we can able to find the path of the magnetic field lines. Here also, to find the electric field, we have to put here one small positive charge. So if I kept a small positive charge, it will repel it. If I kept it here, it will repel in this direction. Okay, so in which point I have to keep here, it will repel. Okay, and that will be the direction of the magnetic field lines of a positive charge. If I have taken a negative charge here, so nearer to the negative charge, if I have kept one small positive charge, it will attract it. In which direction I will keep, it will attract. So that will be the direction of magnetic field lines of negative charge. If I am talking about a dipole, assume here it is a positive charge, here it is a negative charge, and the distance between them is constant, and the magnitude of the charges are also constant. So from positive to negative, just like the bar magnet we have seen, positive to negative, and see, they will never intersect each other. Exactly similar to the bar magnet, what we have learned earlier. Okay, if I'm talking about the charge is distributed linearly, so assume the charge is distributed here. So there the magnetic field lines will be like this. Simple thing you have to remember, you have to put a positive, small positive charge here. So if you put a small positive charge, it will repel it. So as will repel in this two direction only, it is possible. Okay, if you have taken two plates of different charges, assume it is positive and it is negative, so then for middle it is parallel, but at the end they have to take a curve from positive to negative. So that is basically the magnetic field lines. Okay, clear? I think it is obviously clear for you. But my suggestion is that you have to read the definition as well as the properties. Okay, the properties, it is not possible to write it down here, but in your book it is written, you have to read it. Okay, now we have to do the last part of today's work, that is electric flux. Electric flux. Okay, before learning about anything on electric flux, we have to learn one more thing, that is area vector. What is area vector? I'm clear here. See, if I'm talking about the length of an object or volume of an object, we can easily tell it by measuring a scale or by measuring by any other method, because there only magnitude is needed to represent it. But assume if I am talking about the area. So area, by listening, it seems to be a scalar quantity. But area is not a scalar quantity. Assume this is a surface. Okay. And if I want to find the direction of the surface, we have to find a smaller portion on it. So assume that smaller portion we have taken, its magnitude is ds. What will be its direction? The direction will be the normal which is acting perpendicular on it, and that will be the direction. So we can say along this direction the ds vector works. I'm giving you a simple example. Assume if I have taken one any one substance, just like you assume a diary. Okay, so it's a diary, it is the surface. So what will be its direction? It will be along its normal. Okay, what we have seen. And as the surface is moved, you see the direction of normal is also changed. The direction of normal is also changed as the surface is moving. Okay, so that's why we have taken area is a vector quantity, and the direction of this vector quantity should be along its normal, and the magnitude will be the magnitude of the area. Why we should learn this? Because the next part we're going to learn, that is electric flux. What electric flux tells us? The electric flux tells us that it is number of electric field lines along a surface normally. Number of electric field lines along a surface normally. What is it? So assume one surface is given here. Okay, it is one surface. The direction of electric field is acting here. So this is the direction of the electric field. Clear? That is your E is acting. What will be the electric flux? So to find the electric flux, we have to find the smaller surface here. So assume we have to take a smaller surface ds. What will be the direction of ds? The direction of the ds is this. There the ds vector is acting. The E is acting in this direction. Okay, so there will be an angle between them. That angle is theta. So if I want to find out component of E acting along ds, how much component of E is acting along ds? If the magnitude is E here, we can take it is E cos theta. So for smaller portion dx, the flux for ds we have taken it is d phi. Generally we have denote flux by phi. Okay, or phi e, as it is talking about electric flux, but here we are assuming that it is a smaller surface ds, so that's why we have taken a smaller flux d phi e. So that is equals to E cos theta into ds, or we can write down E ds cos theta. E ds cos theta, simply it make us remember the dot product. So we can write down d phi E equals to E dot ds vectorically, because E is a vector quantity, ds is a vector quantity. As we have making a dot product, we will get the electric flux, and phi E should be the integration of it, integration of E dot ds. Okay, if I want to find out flux for a closed surface, means here the surface is open, assume the surface is like this and one charge is kept here, and due to that electric field is acting if a charge q is there. So for closed surface, instead whatever the phi e we have taken, instead of integration we have taken a closed circle integration. This sign you have to remember, one integration sign along with a circle. It is called closed circle integration or closed surface integration, that is E dot ds. Okay, now we're coming to here. As it is a dot product, so it will be a scalar quantity. So electric flux, it is a scalar quantity. If I'm talking about the SI unit here, so SI unit is, that is the unit of electric field and unit of area, that is Newton per Coulomb into area is meter square. So Newton meter square Coulomb inverse. One more unit is there, as it can be written as volt per meter into meter square. So it is volt into meter. Both the unit represents the electric flux. Okay, so it is a scalar quantity, it doesn't have any direction. Okay, my suggestion is just go through the book, read this portion properly. Okay, and if any doubt you can ask, I'll help you. Thank you.